G'day guys, welcome back. I've got another math puzzle for you. Imagine you're at a beach and you're trying to run from point A to point B in the least amount of time possible. So this right here is our crudely drawn beach, this right here is point A, and this right here is point B. Now we notice the closer to the water you are, the faster your speed. So what that means is, as you get closer and closer to the sea, so as y increases, your speed, v, will also increase, right? And that's given by this formula. V is equal to 5y plus 10. Now my question to you is, what path should you take? Do you take the path which involves the shortest distance, or do you take the path which runs along the coast for longer when you're running at a faster speed, right? The choice is yours. Use maths to prove it. Good luck and come back when you're done. Okay, well let's first get started with path 1, right? And I'm going to break this into two parts. I'm going to break it into this part of the journey from here to here, and then from here to here, okay? So let's first consider this part, this part. Your speed, if you're running purely in the vertical along y, is just going to be given as dy dt. And that's only in the case where you're running purely up, right, like this, okay? So v is going to be equal to dy dt, and that's going to be equal to 5y plus 10, given by this formula, okay? Now, integrating this is what we need to do next. So let's bring this guy into here, and let's bring the dt on the top. So this is going to turn into the integral of 1 over 5y plus 10 dy is going to be equal to the integral of 1 dt. And don't forget our limits of integration. We're going to be limiting y from 0 to 1 kilometer. So from 0 to 1 kilometer. And we're going to be integrating t from 0, when we're starting our experiment, to what I will call t1, the time it takes to get from here to here. Now, integrating this will involve the natural logarithm. So we know this will boil down into 1/5 times the natural log of 5y plus 10. And don't forget those limits. We're integrating from 0 to 1. And then on the right-hand side, we'll just get t1 minus 0. Now, integrating this isn't going to be too hard. We can factor out the 1/5, and we can write this as log of 5 times by 1 plus 10, so log 15, minus log of 0 plus 10, which is log 10, right? And that's going to be equal to t1, the time it takes to get from here to here. Now, of course, if we subtract logs, that's the same thing as dividing what's inside of them. So we can write this as 1/5 times the natural log of 15 on 10, or if we like, 3 on 2, right? And that's going to be equal to t1, okay? So far, so good. We found an expression for running from here to here. Now we need to include the time it takes to run from here to here, which is actually pretty easy, right? And it's easy because we're running at a constant speed all the way along here. Remember, speed is going to be equal to distance divided by time, and because v is constant at this point, specifically v will be equal to 5 times 1 plus 10, 15. So that means t2, the time it takes to get from here to here, will be equal to your distance, 1 kilometer, from here to here, divided by your speed, 15. Which means that the total time it takes to run all the way along path 1 will be equal to t1 plus t2, which will be equal to 1/5 times the natural log of 3 on 2 plus 1/15, which is approximately equal to 0.15 hours. That is the time it takes to run along path 1. Okay, now that we've got path 1 sorted, I think the next logical step would be to do path 2. So let's get started. Path 2. Okay, now it's a little bit harder, right? Because v, in the general case, is going to be equal to ds dt, right? We're running along a slope, so that means that v is going to be equal to ds dt in the general case, right? Where s is just the distance along your path to where you are at any point in time t. So v is going to be equal to ds dt, which is going to be equal to 5y plus 10, okay? Now integrating this is a little bit tough. We need to find ds. Fortunately, we've got Pythagoras on our side. We know that ds is going to be equal to the square root of dx squared plus dy squared, right? And then we can also write this as the square root of 1 plus dy dx squared plus, times dx, right? And we can find dy dx because we know the equation of our path, right? This is a direct line, right? And not only is it a direct line, it's a very easy line because this is 1 kilometer, this is 1 kilometer. This actually forms the line y is equal to x. Y is equal to x, right? So in this case, when you differentiate, you can tell that dy dx is going to be equal to 1, right? So that means ds is going to be equal to the square root of 1 plus 1 squared, the square root of 2, times by dx, okay? And we're not done. We can also say that dx is actually also equal to dy when you multiply over. So that means we can write this as the square root of 2 times by dy, okay? So all of this so far has just been to find ds. Let's plug it back into here, and we can now write this as the square root of 2 times by dy dt is going to be equal to 5y plus 10, okay? And this is the differential equation which governs the time taken to go along path 2. And you'll find that it looks very familiar to this one we've already evaluated. So to save time, right, I'm just going to write the answer because we've already done the process. There's just the square root of 2 here. So the answer will actually be the square root of 2 divided by 5 times by the natural log of 3 on 2. And that's going to be equal to the time taken. Okay? We've already solved this using the previous path. Okay? So that means your time taken for path 2 is going to be equal to the square root of 2 divided by 5 times by the natural log of 3 on 2, which is approximately equal to 0.11 hours. So by direct comparison, you can tell that path 2 is the fastest. So this is our winner. This is our winner. Path 2 is the winner. Okay, that's the answer to this problem, guys. I hope you got that. It was a little bit of calculating, it was a little bit of complicated calculus, but we did in the end. Now, before I end this video, I want to briefly mention that if you're kind of weird like me and you need some type of numerical confirmation for your answers, right, then you can actually generalize this on an Excel spreadsheet like I've done. Right, and these right here are just our generalized variables. And you can see I've plotted our line, basically path 2, and this what I've called a square, which is what we've called path 1, right? And by playing around with these values, you can actually generalize the time it takes, okay? And if you're interested, you're probably not, but if you are interested, I'll share this in the description so you can play around with it. Okay, well that's the answer, guys. I hope you really enjoyed that video. Just so you know, I also do videos in engineering, dynamics, statics, and vibrations, so check them out on my website if you like. Cheers.